Hello, my name is Audie, and I'm going to be presenting a tutorial video on the C3d code predicting radiation from a hydrogen flare. Now, hydrogen flare or hydrogen gas in combustion is actually somewhat difficult to model because the density of the gas is very low. It's say 1/14th at room temperature, and then when you heat it up over 2000 Kelvin, it's going to be significantly lower than the surrounding air. So right at the edge of the flare in the combustion zone, you're going to have very steep temperature gradients, and that corresponds to steep density gradients. And both of those result in a fairly computationally challenging situation. Now, the other thing that's somewhat challenging with hydrogen gas is that it is neither optically thick nor optically thin, at least in the dimensional scale that we have of a flare, which is many meters thick. The emissivity of the flare is on the order of about 0.1, and that also is a computationally challenging situation to analyze. Nevertheless, I'll show you how to do it with the C3d code. Now, I'm also going to present three different methods of building the flare. The first one is the most obvious, which you have a tall stack with a hole in the middle, and you inject hydrogen gas in the bottom of the stack, comes out the top and burns. The second method, I'm going to use a solid stack with just a surface source off of a solid at the top of the stack. And the third one, I'm going to use a group of line sources that you would normally use with a nozzle, and they will be injecting hydrogen gas over a short length, and that would be a third method of modeling the flare. Now, the video that you're looking at is basically what's going to be set up. Let me see. You have the coordinate system here. The stack is going to be located at x and y equals 0, as z equals 0 as well. And there's going to be a wind blowing in the x direction of the value that was measured experimentally. And about a little less than 1 pound per second of hydrogen gas is going to be injected into the bottom of the stack. The colors that you see on this ground surface are the heat fluxes in BTU per hour foot squared, shown over here in this color bar. You can see that they vary wildly in time, and that's primarily because of the puffing nature of the hydrogen gas. It comes off in discrete puffs, which are both bright and not so bright. So what you're looking at here is the paper that has the data that we're going to compare to. This was made in 1985. Back then they were interested in the space shuttle, which burned hydrogen as one of its main engines. And when you were using hydrogen, a lot of times you needed to get rid of any excess hydrogen. And what they were concerned with is that when they would burn that, would the radiation from that hydrogen flare be a problem for personnel and equipment on the ground near the flare? This paper was presented back in 1985, and I'll quickly go through and show you the data that they had. What they had done was, here's the stack, here's the hydrogen flare, and they had set up a bunch of radiometers on the ground, presumably looking upward. And there's some other things that they looked at. What they were trying to do is to come up with an analytical method of predicting the radiation. So here's what they had set up as far as the radiometers that measure the radiation. They had, it looks like a total of 8 of them. I'm only going to look at 4 of them. This one, and this one. just for convenience. And the wind was not exactly downwind. It was a little bit, well, you can see the direction that they estimated for the wind. The wind was not measured right next to the flare stack. It was 100 or 200 feet away, so it was a close approximation to what it was. All these units that you see here are in feet. Distances gives you an idea of the scale of the flare. This calorimeter is 45 feet away. This one's 60, and this one is an additional 30 feet. So what do we have? We have 75 feet away from the flare stack. And let me go down a little bit further and I'll show you the measurements that they made. Here we have the data that they measured. These are obviously time averages, and the heat fluxes that they measured were in BTUs per foot squared hour. You can see the range. It's looks like from about, well, here's a low one down below 100, and the highest is 381. But again, we're going to be looking at this set right here, varying from 350 to a low of 138. So in order to set up the problem, we're going to use the C3d GUI. And what we're going to do is create a new project. It'll be a combustion model of hydrogen gas. And now we're going to go in and modify the file that was just read out of the default folder. The time step for the very first time you run it will be set to a single time step just to see if it runs. The equations are set up for combustion of hydrogen gas, for that matter. Let's go into fire model and I'll show you. We only have a single chemical reaction, hydrogen plus oxygen, going to water. Let's see. So in order to construct it, we're going to have a few materials. Right now we have insulator 1, which we're going to use to build the ground surface. And it's actually an insulator here, but we're going to map it to subgrids, which will have the real material properties. So we also need to get some other materials in order to continue building it. So we'll get another insulator for the stack, and we'll get concrete for the ground surface, and let's build the stack out of steel. Okay, so now we have 4 materials. Let's call this one insulator 2. Okay, now the concrete, it comes with a surface emissivity of 0, but in order to have it accept radiation, we have to give it an emissivity. I know the emissivity is not exactly 1, but for this demonstration problem, we're going to set it to be that. The same thing with the steel, we're going to set that to an emissivity of 1. So that pretty much is all the materials that we're going to need. The next thing we need are some gases. We're going to have air. Looks like it's set up correctly. No hydrogen, no water. Mass fraction of oxygen 1 at atmospheric pressure. These are in Pascal. Everything in this code is in standard international SI units. And the hydrogen, again, the mass fraction of hydrogen is 1. We're going to be using this for fuel. Oxygen 0, hydrogen 0. The hydrogen is going to be injected at a higher temperature, so we'll call it 350 Kelvin. And that will be what we use for that. We're probably going to give the air some initial velocity. I'm not sure exactly what they are yet, but we'll come back and edit that later on. Okay, so we've done that. So the next thing that needs to be done is to set up the geometry. Let me click on geometry. For the computational domain, let me go back to the paper for a second. what we're going to do is to set up, I'll go back to this setup here. This is going to be in the X direction, downwind. This will be crosswind, the Y direction. And Z will be coming out of the paper. This is the view looking down from above. So we put that away. So we'll go in there. Now, that was in feet. Everything in C3d is going to be in meters. So we're going to go from a X dimension of, say, -5 to a maximum of 30 meters. And that should cover all of the flare in the X direction. Y dimensions will, again, we'll go from -5 to 15 meters. That's the crosswind direction. And Z will go from 0 to, let's go to 35 meters. And we're going to fill it with air. And that should be all that we need for this setup. Next, we're going to set up the ground. So we right-click, click on Add. It'll be a rectangular region. Call it Ground. And the dimensions will be basically the same as in the domain, from 0 to 30 in, 30 in the X direction, -5 to 30 in the Y direction, no, 15 in the Y direction, 0 to 0.1. So we're going to make the ground 0.1 thickness. And let's see, we don't really need air, but we'll just leave that as it is. It won't change anything. We're going to make the ground out of insulator 1. Now we're going to map that to a subgrid later that will have the real ground properties. So we're done there. Now we want to put in the stack. Now for this first run, we're going to have a hollow stack. So we need to create a solid material and then hollow it out as the next step. So we'll call this solid stack. It's going to be a cylinder in the Z direction, and the X and Y position is 0, 0. It starts at 0. Well, let's have it start above the ground, 0.1 to 15. That would be the height of the stack. And we're going to make that out of insulator 2. The radius will be, the inner radius is 0.22, so we'll make this 0.32, 0.32. And this again is in meters. And that all looks correct. Now the next thing we need to do is to hollow that out. So again, it's another cylinder, hollow cylinder. Z direction. Again, it's centered at 0, 0. And it goes from the very bottom of the domain, because we want to cut the hole through the ground as well, up to the top, 15. And it's going to be hydrogen gas, so we don't have to fill it. And that radius is the inner diameter of that stack in the experimental paper, or 0.22 meters in radius. Okay, that about does it for the geometry. Okay, so the next thing that we need to set up are the boundary conditions. Let me go over what the default boundary conditions are. We have species boundary conditions on all faces. They're all set to 0, mass fraction of 0, but we want to inject oxygen, so that value is 0.233. And these are mass fractions, not mole fractions. So that would be air. For flow rates, we have a flow rate of 0 everywhere at 300 Kelvin. Now what we want to do is set up a wind. in fact, the wind that was specified in the paper. So that's the wind will be a momentum boundary condition. Wind. Let me put in the values that they gave in the paper. I've converted it over to meters per second, so it's 2.8 meters per second. The y component is 0.5 and the z component is 0. Okay, so now we have these three boundary conditions and they apply to all faces. Now what we want to do is change the boundary condition on the bottom so that it will be injecting hydrogen gas. Now, as you might recall, we put in a ground surface, so any flow condition on adjacent to a solid surface will not apply it because you can't flow into a solid surface. However, we did hollow the stack out, so there is a hole in the bottom, and whatever mass flux we apply there will go through the hole. So let's pick mass flux and temperature. It's going to be a value of 1.99 kilograms per meter squared per second, and the temperature will be 350 Kelvin. And it's going to be hydrogen, but we don't specify that here. We have, we want this to apply only on the Z-min boundary at the bottom. So what happens here is that this Z-min will overwrite the Z-min in all of these other boundaries to be this mass flux and temperature boundary condition. We haven't overwritten the mass fraction yet, so we need to do that next. Z-min, it'll be a species boundary condition, and it's going, that's energy species, and it will be mass fraction. The hydrogen mass fraction is going to be T1, and the others will be 0 and 0. So now we are injecting hydrogen gas at the bottom at those specified rates. So this should cover it for all of our boundary conditions. Oh, one more. We need to have the gas flow out the top. So what we're going to do is to put in a hydrostatic pressure boundary condition there with a temperature. No, let's call it 300 Kelvin, not 9900. Okay, so this will overwrite the boundary condition that we had previously at the top with a hydrostatic pressure. So that covers it for all of our boundary conditions. I just noticed that the boundary condition on the bottom surface, on the top surface is hydrostatic pressure. However, it says all, so I got to fix that. It really needs to be Z max, which is the top surface. There we go. And we're done with the boundary conditions. Okay, now the next step is to create a mesh. So I'll click on mesh, and we have to do it in all three directions, X, Y, and Z. This was the default that it came in with, but the best way to do it is to allow the code to scan the geometry and find points that are relevant that you want to map to. Okay, so the way you scan the geometry is you right-click, click on Delete Scan Mesh, go ahead and delete all your old records, and then input a estimate of the number of cells. So I've done that. You can change the number of cells so your estimate is not really that important. So what it did during the scan is it went from the beginning of the domain to the edge of the stack, through the wall of the stack, from the internal diameter of the stack, again the other wall of the stack, and out to from the edge of the other side of the stack all the way to the end of the grid. So there's not a lot going on, so we're going to put a negative direction power law, and 6 cells is okay for that. We're going to put in 2 cells for the thickness of the wall, and the reason for that is if you put in 1 cell, there's a high chance it's going to leak on the diagonal portions of the stack. But if you put in 2, then it won't leak. I know that from experience. And let's put in 6 cells across the inner diameter of the stack and 2 cells there. And we'll put in 41 there for the, well, let's make it a little less so it runs faster. We'll say 30. And so that does it for the x-axis. What we want to do is use a positive direction power law. What that does is it stretches the grid so that you get a nice uniform growing grid. Fixed grid in these dimensions is good. We'll go to the y direction, do the same thing, delete scan mesh, give it an estimate of say 50 again. Now it's done the same thing. Here we can use 7 and a negative direction power law so that it grows in the negative direction. Here through the wall of the stack we want to have 2. Here it went from there to 0 to the center of the opening. So we'll put in 3 in order to match what we have on the x dimension so that we have square cells. And we'll put in 2 through the wall of the stack again. And let's do 25 in the y direction. So that does it for the y direction. Now for the z direction, let's do the same thing again. Delete scan mesh. Yes. Put in 50. Okay, so here's the ground. One cell in the ground is just fine. There's very little going on there. Let's just put in a few cells here and we'll make it grow in the negative x direction. Now, well, in order for it to grow, it needs a starting cell, and we don't really have one if we use a positive direction power law here. So all we need to do is to insert a point, and we'll call it stack exit, and we'll make it 15.1. And so what it's done is that's inserted at a point at 15.1. So now we have a 0.1 thickness cell at this location, just at the exit. And so now we can use a positive direction power law and a fixed width. Let's use 1 cell and let's use, say, 30. Whoops, 30. Okay, so now we have a fixed width, positive power law, negative power law, and a fixed width. So that pretty much does it for meshing the geometry. Okay, so let's go, we'll go ahead and save the data. Okay, and we'd like to run it for one time step just to see if the mesh looks okay. So we go out to run, click on run. It looks like it's running with more than one time step, but let's view the mesh. I had changed the number of time steps earlier without letting anyone know. So the mesh looks okay. You can see how it's stretched in the negative y direction. There's a lot of stretching going on, but there's really nothing going on down here other than flow coming up through the stack. This region here is resolved pretty well, and we want that in order to get the radiation down on the ground. And you can see that well, it doesn't appear to be stretched in the y direction. That looks like a fixed grid, so I'm going to go back and stretch it in the y direction. And then we can come back and test it again. So let's go to close this, modify, go back to mesh. The y direction, right, it's a fixed width. We want that to be a positive direction power law. Save that, run it again. We'll go ahead and kill that, and then view the mesh again. And you can see that the grid is stretched real nicely in the y direction. It's very coarse in the negative y and the negative x because the wind is blowing in this direction where we have the finer grid. And of course the plume is going to go upwards. So all that looks good. All right, so our model looked okay. We're going to close this and go back to modify and continue. Now we're going to add the subgrid for the ground. Right click, add subgrid, and we're going to call it ground. Part name, we'll just call it GND. Length, let's make it 1 foot long, 0.3 meters, and we'll give it 5 cells. The fluid will be air, and the solid's going to be concrete. We have to clip on some boundary conditions, and it'll be adiabatic no flow. Those are the defaults, and we'll just take the defaults. We've got air, concrete, and we're going to do auto coupling. And we're going to couple it to insulator 1. That was what we built the ground out of. And we're going to search the entire domain for that material. So that should cover that. I don't think we're going to couple to the stack. We'll leave that alone. So we're just going to get ground fluxes. The next thing we need to do is a little bit of output. Now the defaults for the contour slices will go through the coordinate 0, 0. We're going to get VTK files for making videos. Let's make it 0.03 so that it's a normal video speed. Let's see, 3D history. I guess we can add that. Now, the one thing we do want to add is radiation monitors. So radiation monitors will allow you to input a table of locations and direction cosines that will allow you to monitor the radiation at that location. And so for this, if I bring up the paper again, let me show you where they were. Here they are. We're going to do 1, 2, 3, 4. Those locations, we're going to input those locations into the table here. So X position, the first one was 15, 15, and we'll pick a location, say 0.2, which is just above the ground surface. The direction cosines of that surface are 0, 0, 1. And that means that that radiation surface is pointing upwards. I'm going to pause the video while I go ahead and input the other values, since there's no need for you to watch me doing that. Okay, so I finished inputting the values. Those are the values converted to meters that were shown in the table. They're all just slightly above the ground, and the surfaces are pointed straight up. Okay, so I think now we have everything we need to go ahead and actually run this problem. Save the data, and we'll go ahead. Let me just check one last time. Yep, it does run. Okay, so now we'll go back, modify the time step. We'll put in a stop time of 5 seconds. We'll print every 5 time steps, and we'll put in, say, 100,000 steps. It'll never reach that, but we'll put that in anyway. I have run this problem before, so I know that 5 milliseconds is too long because it's hydrogen gas. We'll put in 0.3 e minus 3, so 0.3 milliseconds with a min of 10 to the minus 4. Let's put in a half, 0.5 e minus 4. Okay, out to 5. Okay, go ahead and do that. Save data. Okay, now we're just going to let it run. As you can see, it's running okay. Well, let me describe the output a little bit. It shows you the time step. It's called end step. We got some high-speed flow going on. That's the Courant limit. Then this is the time. We have the growth, it's growing, and this is the error in the equation of state, and the cell number, its location. You can see it's either 0 or growing. Here the time step is growing. Here you go, the equation of state error limit. Here it's a velocity limit. So right at the beginning there's a lot of activity going on because it's having a rough time dealing with all of the sudden changes. It does smooth out after a bunch of time steps, and then you get a nice looking flare. So I'm going to pause this video while it runs, and I'll come back later when it's done and show you the results. So that problem takes a few hours to complete, but now let me show you the result. We'll go back into XPlot. Here's the radiation monitors that were set up. You can see they're in watts per meter squared. And of course the paper was in BTUs per hour foot squared. So I've made a file that contains a converted one so that we can compare it directly. And I also included the data out of the paper. So the paper for the black curve, it had 352 BTU per hour foot squared, which is right about here. And you can see that the black data, well, it goes through a transient, but then it starts to steady out. It's a little bit below, just slightly below the measured data. The blue curve, 253, which is right here. And that one actually looks okay. It looks like it's right in what they measured. The green curve, 193, that would be at 200. That too is pretty close to what they measured. And the final one, 138, which is pretty far away, is down in here. So it's a little bit high. Yeah, it's a little bit high, the prediction, compared to what they measured. Now bear in mind, though, the one thing that they did not know is what was the wind at the stack, and they also did not report if they had oriented the calorimeters to be pointed at the flare or just straight up. So there are some defects between what's reported in the paper and what we see here. But in general, you can see that the heat fluxes that are predicted are quite reasonable compared to what they actually measured. The next thing I want to do is to show you the other method of setting up, or the other two methods for that matter, of setting up the problem. The next one will be using a surface source. Let me quit out of here. Close this. Okay, so we're back into the modify. Now we're going to go into the geometry, and this solid stack, we're going to delete that because it's larger than what we actually had. So we'll delete that, and we'll go in and modify the hollow cylinder to be insulator 2. So now it's solid, made of insulator 2. We'll call it solid cylinder. And it's the right diameter, solid fill, all the same dimensions. Okay. Now we're done with that. Now all we do is we need to modify the subgrid to include flow off the top. So we'll call this stack top. And let's see, we'll call this top. And it doesn't matter what length you use. We're going to use one, and we're going to use one cell. If I didn't even spell that right, top, T-O-P. The length is irrelevant. If you use one cell, whatever flows in one boundary flows out the top. So the fluid is going to be hydrogen gas. And let's see, the X-min boundary. So the X-min boundary is going to be the inflow, and we'll use the same inflow we did with the hollow stack. So we'll double click at the X-min boundary. It's combined. It'll be mass flux and temperature. That was 1.99 kilograms per meter squared second. And the temperature, again, 350. Okay, now on the outlet boundary, we have to tell it that it's going into the 3D domain, and that, I believe it's, no, it's going to be a momentum boundary condition. Yes, the 3D pressure, and that will force the flow that's going into that subgrid out into the 3D domain. It's hydrogen gas. Okay, now we have to couple it. The material, we built it out of insulator 2, and we're going to use 0 so it searches over all of the X, all of the Y. Now we want to locate just the top surface, so do 14 point, remember it's 15 meters high, and 15.01. So the top of the stack is exactly 15 meters, so those two Z dimensions will grab that top surface. Okay, we're done here. Now we got to go into mesh. I think we can leave, well, let's change this back to 1. We don't need, there's nothing, we're going to have a little bit of grid, but we're just going to make it easy. There's no reason to try and use 2 there because the stack is solid. We don't need to try and keep it from leaking because there's nothing to leak. Okay, so that's okay. And I believe everything is good now. So we'll save that data. Okay, and let's run it and make sure it runs. Oh, I need to make sure it runs from time 0 because we've changed everything. So it's a write restart. And we can use all the same parameters. Save data. And then run it. Okay, something's wrong. It could not find couple model 2. Okay, so I've got to close this, and there's something wrong with the geometry cylinder. Well, there's the problem. Somehow the cylinder axis got switched. The cylinder is a Z cylinder, not an X cylinder. I think that's a bug in the GUI, but so there's things you got to watch out for. Okay, save data. Okay, and then run it. Okay, so that seemed to work. Somehow that cylinder axis got switched from Z to X during the delete, and I'm not sure what caused it, but I did find the error. So I'm going to let this run. Okay, so that particular problem with the surface source has run to completion, and I'll show you the result. Again, I've set up a plot file so we can compare it to BTU per hour foot squared. And here's the result using a surface source. And you can see, again, the results are basically the same as they were in the previous source where we injected fuel through a hole in the ground up through the stack. You can compare the numbers. They're very close to what they were in the other case. So these are consistent in terms of results. Now the next thing we need to do is to set up the third type of problem where we inject the hydrogen gas as a nozzle. Okay, so now we go back to modify, and what we want to do is modify the stack top to be, instead of auto coupling, we want to use a user coupling file, and we're going to use a file called nozzle.inp, nozzle.inp, input file, and what it will basically leave all the rest of it the same. including the mass flux and temperature. Okay. Okay. Save data. Now, what I want to do is show you what the nozzle.inp file looks like. I have to go to a different place. Here it is. It's a fairly simple file. This was actually created for a nozzle. The first number here, 120, means that there's 120 sources. This is the X, Y, and Z locations. These are the direction cosines. And these are the area of that line source. And this is the length of the line source. This actually came from a file that was a nozzle of a large ground flare blowing upwards, and these are the hole diameters in that nozzle. There's 120 holes. However, I did modify it so that it was the same diameter, and you can see there's just goes down and down. This isn't exactly what we want, but it was good enough for a demonstration, and that's all I wanted to do here was to demonstrate. So now that we have this, I'll go ahead and oh, I have to bring that in there. So I'm going to hit pause and move some files around. Okay, so I have moved the nozzle.inp file into the directory containing this run. So now I'll just go ahead and run it. And it runs, and all we did was move in a file and tell it how to couple that file. So we'll just go ahead and let this run, then I'll show you the difference in what a line source looks like. So the calculation is pretty much finished after a few hours, and I'd like to show the results. So let me bring up XPlot. It jumps to the back again, but here we go. So first, let me show you what the source looks like. We'll go to Y center and the mass source. You can see the stack here. Let me freeze this. And there's the source. There are short line sources, 1 meter in length, and they're injecting hydrogen gas. And here's basically the hydrogen flare that we get showing gas temperature. So that gives you an idea of what it's like. And now let's take a look at the radiation that was being predicted. Just like in the other cases, you can see it's all in the same range. The 350 is right about here, and you can see the black line is the average is a little bit low. 253, which is right here. The blue line is right in the middle. 193. That's around 200. Yeah, the green line is right there, and the 138 is a little bit high. So it's basically the same result as was obtained in all of the other cases. One thing you might note is the variation in the radiation flux. It's actually quite large. Looks like about 30%. So, and this is due to the puffing of the hydrogen flare. So that pretty much closes or finishes this presentation that I wanted to show 3 different ways of predicting a hydrogen flare and comparing it to experimental data, which shows that the code is predicting answers right in line with what you would expect compared to measurements. And so that concludes this tutorial.